So in this video, we're going to use the properties of determinants that we looked at in the previous video, or the properties of determinants under matrix operations. So suppose A is a 2 by 2 matrix for which the determinant of A is equal to 3. Compute each of the following. So here we have the determinant of 4 times A. And what we would do is use property 1, where if we have a scalar times A, we get the scalar to the nth power, where n is the size of the matrix. So this is a 2 by 2 matrix, so in this case n will equal 2, so we just get 4 squared times the determinant of A using property 1, and that's going to be 16. 4 squared is 16, times the determinant of A, which is 3, so 16 times 3, which is going to be 30 plus 18 is 48. Here we have the determinant of A cubed, and we want to recognize that A cubed is just equal to A times A times A equals, and right here we can use the associative property. We could actually group this into 2 using the associative property, which would give us the determinant of A times the determinant of A. That would be applying property 2. It says if you have the determinant of the product of 2 things, you get the product of the determinants. So using the associative property, I can make this into 2 things and then break it up like this. And then this is going to equal, now this is the product of 2 things. I apply property 2 again to get the determinant of A times the determinant of A times the determinant of A. And there's a proof by induction kind of hiding in here. How would you calculate the determinant of A to the n? And then there's a claim that we could make, that we could prove using induction. So this is just going to equal 3 times 3 times 3, which is just going to equal 27. So here we have the determinant of 3 times A inverse times A transpose. And what we want to recognize is that the 3 can be factored, the 3 can be brought out. It's a 2 by 2 matrix, so we can apply property 1. The 3 can be brought out, and it's going to be to the 2nd power because A inverse and A transpose are 2 by 2 matrices. So we're going to get a 3 squared times A inverse times A transpose. So this is going to be 9 times, and then from there we can get we can break this up. We can use property 2 to say, hey, if we have a product of 2 matrices, we can break this up into the product of the determinants equals, and the determinant of A inverse by property 4 is going to be 1 over the determinant of A, so we get 9 times 1 over 3. And then the determinant of A transpose, we can apply property 3 to say the determinant of A transpose is the same as the determinant of A. So this is going to be 9, a third of 9 is 3 times the determinant of A is 3. We get 3 times 3 is 9. So this one says prove that the determinant given here is the same as A. So you would start with this. We wrap some nice words around it. I'm just going to kind of mechanically run through it. We would go A inverse, A transpose, A. And we can actually use the result that we saw here, where we can, if we have 3 things, we're going to wind up being able to group them and get the individual products. So if I kind of extrapolate from what happened in 2, I can see that this is going to play out and give me this by similar process. And then the determinant of A inverse we know is equal to 1 over the determinant of A times the determinant of A transpose. The determinant of A transpose by property 3 is just the determinant of A. and this is times the determinant of A, and these will give us a 1 over determinant of A times determinant of A is 1. So this simplifies to the determinant of A, which is what we needed to show. And this says prove if A and B are matrices of the same size and A is singular. So if A is singular, that tells us that the determinant of A is equal to 0. Then A times B is singular. So we need to show that the determinant of A times B is equal to 0. So let's start with the determinant of A times B. Here's the determinant of A times B, which by property 2 can be broken into the determinant of A times the determinant of B. We know that the determinant of A, because A is singular, the determinant of A is equal to 0, so we get 0 times the determinant of B, which is 0, and then we would say that because the determinant of AB is 0, AB is singular.